Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So far this week we have understood the fundamental ideas of photonic crystals. So we took the simple case of a 1D photonic crystal and we explained the existence of band gaps and what happens and so on, how do we analytically understand them and all that. So in this last lecture of this week, I will try to show you some examples of how photonic crystals are useful. Alright. So before I go into it, I'll go back to a little bit of a background on the 2D and the 3D photonic crystals, because that's something that we have not yet discussed. I just mentioned that briefly. I won't discuss them in any great detail, but just show you what they are. So we already saw the 1D photonic crystal, which is simply an array of thin films. Then the first immediate problem with that was, we already mentioned that it was not possible to get a band gap in all possible directions. If you have various angles of incidence, you will have electromagnetic waves propagating through the material. It's very difficult to get a omnidirectional band gap. Okay, so the immediate alternative was to think of two-dimensional arrangement of materials. Okay, for example, the first idea was that, one of the first ideas that was explored was, let's say, what if I have a scenario like this? I have a two-dimensional arrangement of, let's say, silicon. Okay, arrangement silicon. So let me call this is silicon rods. Silicon rods. So in the z direction they are kind of infinite. Let me say this is they're going all the way into it. So you have this 2D arrangement of structures like this, rods like this. Okay, silicon rods which are protruding from a surface. Okay, can we have a photonic crystal out of it? Of course, we have different refractive index which is arranged in a periodic way, so we can analyze the band structure of it. The techniques are slightly more complex, but it can be done. Okay, but it turned out that if you take such a scenario of a simple rods which are protruding out of surface, it was not sufficient. So the next alternative people thought about was, what if I have, let's say, a substrate and I make holes. Okay, let's say this is my silicon substrate. Okay, silicon substrate. Right, and this is let's say this is 3-dimensional substrate. Okay, it's kind of understood. When I have that 3-dimensional substrate, now I'll make air holes in this. So basically I'll create structures. Let's say this is air. Okay, so these are, let's say, air holes. So I have a substrate. I'm creating the inverse structure. In the first case, we took pillars which are protruding out of the substrate. Now we can think of holes which are in a substrate. Okay, electromagnetically they are similar. Okay, but it turns out that one of them actually exhibits a band gap in TE mode, other one exhibits in the TM mode. So and it was difficult to actually create a photonic band gap for all possible polarizations and angles of incidence. So finally, scientists came up with the idea of hexagonal or triangular hexagonal arrangement of holes, which is shown on the right here. So this is a picture. So what essentially they are doing is, you have a substrate which is, let's say, dielectric constant again, just for sake of simplicity, 13. Let's take this and we drill it with holes. Okay, we make holes. How do we make it? We'll not cover right now, but let's say we can make it, and you essentially end up with holes which are arranged into the lattice like this, and they are having a separate, they are having a particular arrangement of hexagonal lattice. Okay, it turns out that when you have a such structure like this, you can have a photonic band gap for all possible angles of incidence. And because it's two-dimensional geometry, the band structure becomes slightly more complicated, and we'll have to talk of the high symmetry points like gamma, m, k, and so on, which you may have already seen in electronics. But essentially, the most important feature is there is this band gap that is open for, all possible, let's say, angles of incidence. Okay, so this is one of the features, omnidirectional reflector I mentioned. So if you have such a structure, I can have at any angle of incidence and the wave will reflect. You see, it was so difficult actually. If you looked at the T matrix code and try to calculate for a single 1D photonic crystal, try to calculate reflection at particular different angles, you will see that it's very difficult to get reflection, high reflection at all angles. Okay, but in this case of a photonic crystal with a 2D geometry like this, it was possible, and that's one of the I think key successes of this area. Okay, and this became one of the most popular geometry that has been studied by various research groups across the world. All right, so this is in the 2 dimensions. But if I go back to my first slide, wherein I talk about the idea by Jablonovich, who proposed that we should have a photonic crystal in 3 dimensions, and he originally proposed an idea that, okay, this sort of a hexagonal lattice you have, hexagonal lattice, and you want it in 3 dimensions, not just 2 dimensions. Then it turns out that you will have to actually create holes not just in the vertical direction, but you have to create holes in 3 different directions. So what he proposed was, let's take this hexagonal array, and then I'll drill from 1, 2 and 3 directions. At the same point, I'll make holes in 3 different directions, and then I'll create a structure out of it. And of course this involved a lot of analysis in the background, a lot of unique insights, and Jablonovich proposed this, and I think in the year 1991 this was demonstrated, and this structure was called as Jablonovite. Basically, just to pay homage to the person. I mean, he's an amazing engineer, and if you ever happen to get a chance to read his research papers, I would, you'll really be, you learn how to write a research paper. He would really very crisply address all the issues, and his papers are really insightful. So yeah, he proposed this idea of photonic crystal in 3 dimensions, and this was actually realized. And this again had a band gap in in all different directions. So it was a big milestone, and in a way this could be said as the birth of photonic crystals. Okay, but the only problem here was that this was constructed, I believe, out of alumina, and it was the holes that could be drilled in alumina were very large for the tools that they had, and so this was operating in, I think, millimeter wave frequencies. Okay, operates at millimeter waves. For RF millimeter waves, microwaves, it would work, but not in the visible domain, because the sizes are much smaller. So visible frequencies have higher, visible frequencies are higher in energy, right? And so we have to have smaller dimensions. That's what we've been harking back right from the beginning. So this was a 3D photonic crystal, and not only this, after this, there was really a surge in research interest among various groups trying to compete and create artificial photonic crystals. Okay, some of the examples. So it took some time for the people to understand and think about how to do it. But one of the more convenient ways of doing it, especially, I think this was near IR, if I'm not mistaken, visible near IR, close. This basically was the famous wood pile structure, wherein you basically had silicon strips which are arranged, and every alternating layer had perpendicular orientation of the strips, and every 2 layers, I think, were displaced by half period. Okay, and then they made a photonic crystal out of it. This is interesting. I mean, this is essentially in parallel to what you would see in electronics, right? Or in any material. If you take semiconductors, you have this regular arrangement of atoms. Similarly, you have arrangement of these unit strips. So that created the photonic crystal. And then, of course, this is one such technique that finally was implemented in 1998. Okay, already 23 years back. And then you also have others, structures like inverted opals and things like that, which a lot of bottom-up fabrication techniques were explored to create 3D photonic crystals. So, what is the use of all this? Just one more historical fact, that in the year 1996, Krauss and others, they showed one of the first 2D photonic crystals. This was operating at near IR in this case. Okay, so they simply had the same idea of this hexagonal holes which are arranged, and then you can actually drill that hole in let's say gallium arsenide film. Okay, so the challenge has been in the development of photonic crystals, the challenge has been the accessibility of nanofabrication techniques. So whoever had the nanofabrication facilities could do this research, others could not do it. So that was one of the key requirements for this progress in this area. So yeah, it just went on, and just to give you a glimpse of what kind of fabrication is required, So this is, we already showed this wood pile structure. How do we make this structure? The way to do that would be, take a piece of silicon, make an array of silicon dioxide, and then etch it, and then fill that with silicon again. So for example, I'll take this silicon substrate, and then I'll make, initially I'll cover it with silicon dioxide here and here, and then I'll fill it with silicon here. Okay, and then do the same thing. For example, here, initially I would make silicon dioxide, okay, I should write it in red perhaps. Silicon dioxide. So make lines of silicon dioxide. In between, wherever the gaps are there, fill it with silicon. This is what is called as polysilicon. Okay, and then repeat it. You actually finish one layer, planarize it, and then repeat it in the perpendicular direction, and so on, and just keep repeating how many layers you want. Eventually, after the structure is finished, you dip it in HF. HF is hydrofluoric acid. The moment you dip it in HF, all the silicon dioxide gets etched away, and what you have is a structure. In some way, you're creating out of some, a kind of a scaffold consisting of some soluble material, and then you're filling it with various structures. So this was the way that was done, and it was intense. And I've seen PhD students actually working in the lab for almost 4 or 5 years to fabricate these structures. So fabrication is quite intensive in this structure, in these photonic crystals, but they exhibit a lot of new interesting phenomena. So this is about the background. Where are the applications? One of the most prominent applications of photonic crystal ideas is photonic crystal fibers. So we have the regular optical fibers, which have basically a core consisting of a slightly higher refractive index, and a cladding consisting of slightly lower refractive index. And because of the difference in refractive indices, the light undergoes total internal reflection while it propagates to through the fiber, and then it propagates to very large distances. But the traditional fibers have some limitations. So scientists have come up with, especially Philip Russell's group in, I think, UK, they came up with this idea of photonic crystal fibers, wherein they actually make photonic crystals in the fiber. How do they achieve that? Well, what they do is, in the traditional glass in the fiber industry, you have this melt or, preform of glass, and you draw it. You basically have a preform, and then you heat it in a particular zone, and as it gets heated up and melts, it becomes soft, and you basically pull it down. This is called basically drawing tower, they call it, to make fibers. So you draw it, and then you get an optical fiber out of it like this. So what Philip Russell's group did was, they actually took a stack of various preforms like this, let's say in hexagonal arrangement like this, and then heated that stack. And when they pull it, what they end up getting is something like this. You have this glass and holes in between. So the fiber itself has these various holes in the form of whatever we want. So not just holes, depending on how you stack the initial, glass rods, you can have various different structures, consisting of a dielectric core on air and also that. So you can fabricate these photonic crystal fibers. And just another view of it. So yeah, you have the traditional fiber, which is quite simple in some sense. But if you look at a photonic crystal fiber, you can have initial, let's say this is called as a dielectric core, wherein the center of it is basically a high index dielectric or dielectric. And then in the third case, it is basically the air, which is useful in some way. I'll just show you an example of why is it useful. So you have the air core. So basically the light can propagate through this, and all of the surrounding medium is a photonic band gap. So in effect, we saw that light cannot penetrate into the photonic band gap. So now what they have done is take a center line, and then they made sure that light cannot propagate anywhere else. So automatically light goes through the fiber. So this is in contrast to the traditional optical fiber, which actually propagates by total internal reflection. Here there is no total internal reflection, but it is a band gap that exists. So light is because of this, the way the surrounding cladding is arranged, light cannot propagate in that. Okay, this is one of the fantastic achievements. And you might say, why do I care? One of the reasons, one of the examples could be, let's say in the delivery of let's say one of the first lasers that was built was a carbon dioxide laser. It was operating at 10 microns. And the reason it was built was that, it can carry, high power, basically. It was used to burn and, cut things. That was the first application of lasers. So when this carbon dioxide laser was built, if you want to deliver large amounts of power, the fiber would get actually burnt. One of the ways to overcome it is by creating a photonic crystal fiber with a hollow core. When you have such a hollow core, essentially it is air. And how do you create the cladding? In this particular example, they created cladding out of thin layers of various materials. I'm not sure exactly what the materials were, but probably dielectrics, which having alternating layers like this. And once you have such a structure, in the core you do not have any you don't have any material, and the carbon dioxide, it can be tuned in such a way that the carbon dioxide actually carbon dioxide laser line, okay, can propagate through this, and you can have a very strong transmission of it. Okay, so it can guide very strong lights, and it also happens that it does not allow the light or a laser pulse to disperse. So some advantages are there for this hollow structures like this, right? And what you see here is basically transmission as a function of wave numbers. So remember, I introduced wave numbers in the beginning. So this is 1 micron and this is 5 microns. Okay, right? 10,000 divided by 4,000 should be 2.5 microns. This is 2.5 microns. This is 5 microns. So you see that there is this strong propagation of lights, okay, at various wavelengths. This is one application of a photonic crystal fiber. Another application is what is known as supercontinuum generation. So we have all, we see broadband light, which is regular everywhere, the LED lights. But for optical experimentalists, we require a very highly monochromatic source of light, which is a laser. And if you look at, and we also are interested in very, very short pulse laser. For example, we want to have a 10 to 20 femtosecond laser pulse. The reason is, if you confine energy into that 20 femtoseconds, you can get very, very high intensities, and a lot of interesting experiments can be done. Okay, especially in the area of nonlinear optics. So one of the popular femtosecond laser is what is known as a Tie-sapphire laser. Tie-sapphire laser. Okay, and various groups have it. It's a size. It's a big block. We have the amplifier, and then we have the mode locking and things like that, which actually are used to generate the femtosecond laser pulses. Now, if you want to have a laser pulse at all wavelengths, it becomes very, very hard, because Tie-sapphire has a specific gain bandwidth in that region of 800 nanometers. So we have the peak amplitude that comes in at that point. But let's say you want to have output power at various different wavelengths, and we want it to be pulse laser. It becomes very challenging. You might say, oh, I can use a lamp, but lamp has a very low intensity. So we want to have broad range of optical, radiation over a broad range and at high intensities. And the way to do that is this supercontinuum. So what happens in this case is the femtosecond pulse propagates to through a photonic crystal fiber, and because the photonic crystal fiber has very, very strong dispersion, because it's just different materials and lot of if you look at the dispersion of the photonic crystal, because the band gap is so complicated, right? So it exhibits very strong dispersion. So essentially it ends up converting this incident and electromagnetic energy at 800 nanometers into radiation at various broad range of wavelengths. And in this case, I think this is about from 400 nanometers to 1600 nanometers, more than 1400, so almost like close to 1000 nanometers, 1100 nanometers of broad light, which is high intensity and also pulses of high intensity, right? So this is known as a supercontinuum, this particular. So it's actually quite difficult to generate the supercontinuums. If in lab in the past, people used to actually use water, and then you disperse through that, and there were a lot of other techniques that are done, but never they could get this broad supercontinuum before. So photonic crystals were like that way very, very interesting, and the company came out of it. There's a company in Netherlands that sells it, NKT Photonics. But anyway, so this is a lot of interesting applications came out of this. And yeah, lastly, there are various other techniques, because as I said, the fabrication of photonic crystals is quite challenging. So various groups spent a lot of time trying to actually develop self-assembled photonic crystals. So bottom-up approach. Top-down patterning can be very tedious and time-consuming. So people explored how to do that. They use all sorts of methods. So I would refer you to, if you are interested in that, I would refer you to this review and how it is done. All right. So let's not really get into the fabrication, but it turns out that they are able to get reasonably large photonic crystals using this technique. So to sum up, essentially we can think of photonic crystals as semiconductors for light. So whenever you have this 1D, 2D or 3D modulations, they exhibit band gaps similar to what you see in electronic materials. But the only difference is in electronic materials, they are all atomic scale. Now it's much, much larger scale, nanometers or even larger. So you have 1D, 2D, 3D geometries, and they actually control the propagation of electromagnetic waves, just like the semiconductors control the propagation of electronic or electrical signals. And it's a new frontier for photonics. Okay. One of the challenges in this area is that they're very, very sensitive to the fabrication tolerances. So we showed these structures. The moment even there is a slight amount of disorder, that really creates havoc in the optical effects that can be observed. So that has been one of the difficult aspects of photonic crystal fibers. One of the key features is we should have a very strong index contrast to actually observe these band gaps. Otherwise you would not see it. And this is in a way different to what you would have seen in a conventional fiber, wherein the difference between the index of the core and the cladding is very, very small. But in the case of photonic crystals, we want it to be as large as possible, and we can analyze them using concepts very similar to what we use in electronics. All right. So with that, I would take leave, and I'll also try to record a brief demo of how to use, I'm going to host these 1D photonic crystal calculations that I've shown, right? I'll host them on GitHub. I'll just record a brief video I'll show you what it is. And if you're somebody who is going to work on photonic crystals or this directions in your research, please, I'll ask you to go through that, and then you'll also develop a lot of insight. So thank you so much, and take care. Bye.